The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good afternoon. I would like to thank everybody for hanging in there. I'm sure everybody's hungry. And I would like to acknowledge my co-authors. This presentation brings a little bit of data from several studies. That's the reason we have so many co-authors. And one of them is in the audience, Ahmad Ardani. When I went to school, not too long a time ago, okay, I'm not that old, back in Brazil, when I was a teenager in high school, when I first fell in love with concrete, I learned that concrete was coarse, fine, aggregates, cement, and water. Since then, the technical, economical, and nowadays the environmental requirements have changed quite a lot. And we got to a bunch of different things that drive us nuts in the field. So we have admixtures, we have supplementary cementitious materials, we have fillers, we have fibers, and we have our conventional concrete. And nowadays we have been trying to push the envelope more and more to use high volume fly ash mixes. We are not quite there yet, but we have to overcome first some of the challenges: delayed setting, reduced early age strengths, and increased sensitivity to curing conditions. Everybody talked about this in the previous presentations. In the past few years, both NIST and FHWA have been working on high volume fly ashes, and we have some of our studies there. They worked on fine limestone additions, we worked on testing procedures, and together we worked on concrete mixes. So first we started with mortars, we went to concrete, and now we are setting back to pastes. And in this case, we are using nanoparticles as well. So here is most of my talk based on. We have several mixes. We have a PC mix that was based on one of our concrete mixes on the previous study. And we replaced by volume, and we kept the volumes constant. That's very important. So we replaced the cement content by volume by 60%. 60% either F fly ash or Seafly Ash, or a combination of fly ash and 15% of limestone, or fly ash and 1% of different nanoparticles. The nanoparticles, the limestone we had was a 0.7 micrometers, as Waraf had in his presentation. We had Nano Silica, we had Nano Alumina, Nano Bohemite, and we had a combination of Nano Silica and Nano Alumina with different silica to alumina ratio, 0.64 and 1.3. All the nanoparticles were synthesized at Turner Fairbank. And since we kept all the volumes constant, the volume of water is constant for concrete, the water to cement ratio changes in the different groups. Let's have a look at the setting. So here in red is our PC mix. The green, in both cases, it doesn't look very green, but the greens are the fly ash and cement only. And then we have the 15% limestone in blue, and we see we accelerate quite a lot in both fly ash C and fly ash mixes. And we have for the F a 75-minute acceleration, for the C 200-minute acceleration. And we have also another mix that accelerated the setting was the 0.64 silica to alumina ratio, which is this blue here. All the other nanoparticles for F either did not accelerate setting or even delayed slightly. For the Seafly Ash, the Nano Silica accelerated slightly, but not as well as the limestone. So we ran rheology. And our rheology test protocol was, we had a pre-shear, then we increased the shear in 10 steps, and then we decreased the shear in 10 steps. We used this curve to plot shear stress over shear rate. And with this curve, I have the slope as apparent viscosity, and the intercept is our yield stress. Here are the results. Although we ran that protocol at different timings, 10 minutes, 30 minutes, 60 minutes, 90 minutes, 100 minutes, and we want to see how it progressed. For the PC mix, so here we have PC 10, 30, 60, 90, 10, and 120. For the PC mix, although we went only up to 120 minutes, so not close to the setting time. Although we are not close to the setting time, we already see something going on. At 90 minutes, we see a change in the curves. And what's happening here is that the water film thickness around the cement grains is changing. So the solid-solid contacts increase. For the F-fly ash mix, nothing appears to be going on. There is no apparent agglomeration at this point. If we look at the 15% limestone, again, we see something happening at least at 120 minutes. For the Nano Silica, nothing is happening. For the Nano Bohemite, something seems to be happening at 120, but not significant. And then for the silica-alumina ratio of 0.65, definitely something is going on. Not only it's increasing, but the slope of 120 minutes, it's inverted. What's going on? We believe that the agglomerates are forming, and as we increase the shear rate, we break those agglomerates. And when we decrease the shear rate, these agglomerates are capable of reforming. So we have a negative slope, and it gives us an impression of a negative apparent viscosity, which is not possible. We are just really seeing agglomerates are forming. Something in the microstructure is changing. For the silica-alumina ratio of 1.3, nothing seems to be happening again. Class Seafly Ash, nothing happening here, only fly ash. Again, the same thing, limestone is accelerating. Gaurav's talk was all about limestone acceleration, so we don't need to go there. We are just confirming his experiments. It is accelerating, great. In this case, Nano Silica is accelerating, and it confirms our setting time measurements. And Nano Bohemite doesn't seem to help at all. And silica to alumina ratio 1.3 appears to help slightly, but not much. So if we plot yield stress, over the time, we see that for the PC mix, there is a jump between 60 and 90. So something is happening at that time period. For 15% limestone, again, there is a quite significant change. And for the 0.64 silica to alumina ratio, something happens too. For Seafly Ash, again, limestone shows some difference, and Nano Silica shows a little bit of change, and we don't have here 0.64 yet. Colorimetry curves. You probably are tired of colorimetry curves today. I'm so sorry. But colorimetry, isothermal colorimetry, helps us to understand what's going on with the system. So we have first the silicate peak for the PC mix in red and the aluminate peak. When we put fly ash, there is a shift to the right. That is the delayed setting, and the peaks are much lower. When we put limestone, we amplify the aluminate peak, and we shift the curve to the left, helping with the setting time. Because the limestone provides the nucleation sites. So let's see what happens when we put nano silica and nano bohemite. For the nano silica, the aluminate peak is amplified, but the curve shifts to the right even further, so there is a delay setting. And for the nano alumina, nothing seems to be happening. The peaks are even lower, and it didn't shift to the right. When we put the nano, the 0.64 silica to alumina ratio, we have a significant change in the curve. First of all, it shifts to the left, and it matches the PC mix. Second, the aluminate peak is significantly amplified, and it overlaps the silicate peak. And when we put 1.3 silica to alumina ratio, that is again an amplification of the peak, but the shift to the left is not really significant. For the Seafly Ash is again the same thing. Limestone really helps with the setting. And when we put nanoparticles, all of them helped slightly, but not as well as limestone. So what is going on? We have here a PC mix and the two peaks again. And when we put nano silica, again, we have no fly ash there. When we put nano silica, only 0.75% in the previous slides were 1% replacement. We see a significant shift to the left and increase on the amplitude of the peaks. Why? We believe we are providing nucleation sites for CSH and depletion of sulfates due to adsorption on the surface of the nanoparticles. When we add other nanoparticles with different silica to alumina ratio, in this case 1.8 and 0.65, 0.65 is pretty close to the previous slides with 0.64. In this case, 0.65 accelerates the peak by 15 hours. Why? Because on top of what we had before, we have depletion of sulfates with the precipitation of monosulfate. And we also have, in this case, instead of only precipitation or formation of CSH, we have formation of cash. When we add nanobohemite, though, it did not accelerate the peaks. It happened with the fly ash mixes as well. It did not amplify the peaks, but it did deplete the sulfate due to the same two reasons I mentioned before. So what's happening here? If I plot time for the maximum peak of either the silicate peak or the aluminate peak over the silica to alumina ratio, it appears that we have an optimum silica to alumina ratio. If we plot the maximum or the amplitude of the peaks over the same ratio, we also see that there is an optimum silica to alumina ratio. What's happening here is that we measure the pore solution, and the top ones in all cases are only cement. And I will, the triangle ones are the 0.65, which appears to be the optimal. And we see that 8 hours after mixing, there is quite of a difference in the potassium and sodium concentration in the pore solution. It appears that there is alkali binding. Over time, this difference decreases. It appears that the alkalis are going back to the solution. When we look at calcium, though, the difference continues very big, no matter at 8 hours or 72 hours. For the sulfate, we also have quite a big difference at 8 hours, and for the 0.65, it slightly decreases at 72, and for the nanobohemite, it increases even further. So, is there any relation between the concentration of ions and the time that peaks appear? For the silicate peak, yes, it's very clear that there is a relation between concentration of ions and time of when the peak appears. And for the aluminate peaks, there is some correlation, but not as good as with the other peak. Guarav also talked about compressive strength relation with total heat and calorimetry curves. And what we have here is a bunch of studies. We have PC mixes, we have high volume fly ash mixes, we have high volume fly ash mixes with limestone, concrete mixes, mortar mixes. We have different cements. And what we did is total heat, let's say, at 1 day, and compressive strength at 1 day. When we measured compressive strength of concrete, the total heat was measured on the sieved mortar. When we measured the compressive strength of the mortar, the total heat was measured on the mortar or on the paste. And it's a very good correlation. Here is the 95% confidence interval. But for the paste that we just had with the nanoparticles, I didn't have 7-day calorimetry data. I had only up to 72 hours. So I decided to plot differently. I used the 72-hour total heat to come up with other two curves to measure, to predict compressive strength either at 7 days or 28 days. Here are the cumulative hits for the pastes that I just showed. So again, the PC mix has a much lower total heat. The fly ash mix is much lower. They are the green ones. And when we put limestone, we increase the total heat. And in this case, we increased with 1.3 and with 0.64. Here we didn't increase with anything. We predicted the strength, and our main objective is to improve the early strength. And it appears that, again, limestone improves the strength both early age and later age, and we confirmed that with measuring. And for the nanoparticles, we didn't measure. We are going to measure in the near future, but it didn't help at all. Here I have the base for the 3-day, and here for the 7 days. So it's either the same as the fly ash only mix or even worse. Summary: fine limestone, everybody knows already, helps accelerating the reactions, helps with the strength. Nano Silica did accelerate setting, but only for the Seafly Ash. It did not change the cumulative heat, so we don't expect to help with the strength, and provides nucleation sites for CSH. For the nanobohemite, it did not accelerate setting. For neither of the ashes that we tested, it did not improve the cumulative heat, so we don't think it will improve the strength. and it provides a nucleation site for the formation of cash. What we don't know yet is, does cash help with durability? We will see this later. We are not at that point yet. And for the aluminum silicate, it appears to have an optimum silica to alumina ratio of 0.64. It helps accelerating setting, but it doesn't seem to contribute to strength. So it forms cash as well. So bottom line, limestone is better. It's easier. It's cheaper. But if it helps with durability, so we have a plus here. Limestone, we measured in the lab some of the durability tests that we run. It helped as well. So with that, I'm open for questions.